Hi everybody, it's Mrs. Mancuso. I want to do some half-life problems with you. So within nuclear chemistry, we talked about these different radioisotopes on table N and how they naturally decay, naturally transmutate to another element. And this was their decay mode. Well, on table N, it also tells you their half-life. So this is how long it takes for half of the mass of a sample of this element to naturally decay. So we're going to use those numbers in our problems. I figured the easiest way to go through some of these problems is just to grab a worksheet of these problems. So if a sample of cesium-137, sorry, just caught that. If a sample of cesium-137 is stored in waste container in Yucca Mountain, how much time must elapse until only 1/8 of the sample remains unchanged? So if 1/8 remains unchanged, I have to figure out how many half-lives that means. So each half-life, you end up with 1/2 of it. So 2 times 2 is 4, so I haven't done enough half-lives yet. All right, 2 times 2 is 4, times 2 is 8. So that tells me 3 half-lives have gone by. Now I can look up what cesium-137's half-life is. Here it is, 30.2 years. So I want 3 times 30.2. So that would be 90.6 years. So I figured out how many half-lives, 3 half-lives. I figured out how long a half-life is, and I multiplied. That'll tell me how much time has gone by. Approximately what fraction of an original CO60 compound remains after 26.3 years? So 26.3 years have gone by. I want to divide that by the half-life. So I'm going to look up CO60. CO60 is 5.271. So I divide 26.3 divided by 5.271, and I get 5. So that means 5 half-lives have gone by. So that means I need to multiply 1/2 5 times. All right, 2 times 2 is 4, times 2 is 8, times 2 is 16, times 2 is 32. So 1/32 of that sample would remain. After 16 days, 5 milligrams of an 80 milligram sample remains unchanged. What's the half-life? So if I am starting with 80 grams and I'm going down to 5 grams, I need to actually do the arrows. I need to figure out how many arrows or how many half-lives have gone by. So after 1 half-life, I would have 40, so I just cut it in half. After 2 half-lives, I would have 20. After 3 half-lives, I would have 10. And after 4 half-lives, I would have 5. I wanted to end in 5, so there we go. 4 half-lives have gone by. So if 16 days have gone by and I've done 4 half-lives, 16 divided by 4, the half-life must be 4 days. 4 plus 4 is 8, plus another 4 would be 12, plus another 4 would be 16. So 16 days have gone by, the half-life must be 4 days each. All right, how much time must elapse before 16 grams of potassium-37 decays, leaving 1 gram? So I want to start, anytime I'm given grams and grams, start and do your arrows. So after 1 half-life, I'd have 8. After 2 half-lives, I'd have 4. After 3 half-lives, I would have 2. And after 4 half-lives, I would have 1. So 4 half-lives have gone by. And I want to know how much time that is, so I'm going to look up K37's half-life. K37, 1.23 seconds. So 4 times 1.23 seconds is 4.92 seconds. This is an extremely short half-life, so obviously this is going to be gone really fast. All right, so let's just last talk about some commonly used radioisotopes. There are 4 that you should really know. Carbon-14 is for dating once living structures. So like if you find a fossil, that was something that was once alive, or if you find like remnants of a woolly mammoth, a bone. So if you're trying to figure out how old that bone is, it was once living, so you can use carbon-14. I shouldn't say fossil because that's going to be rock and that's not going to work. You have to have a portion of it that actually once was filled with carbon. All right. Iodine-131, that is used for detecting thyroid disorders. And cobalt-60 is used for cancer treatments. So when someone says that they need to get radiation treatments are done with cobalt-60. And then last, uranium-238. It's used for 2 things. It's used for dating rocks. So now I can go to my fossil idea. If I have something that is really old that doesn't contain the once living thing anymore, but it's more just an imprint, I can figure out how old that rock is using uranium. Or this is also used for nuclear fission in power plants. Nuclear reactions are amazing because they make so much energy. And there's a very slight loss of mass, but a massive amount of energy produced. So nuclear reactions are always known for their great output of energy. Thanks for joining me.